By the end of this video, we will have talked about the idea of a differential equation. We'll see some examples of differential equations, but we're also going to talk about what it means to be a solution to a differential equation. Before we get into that, though, I want to think about the idea of a solution to a different kind of equation. So this will be more of a recap of something well before this course. So if I were to ask the following question, is 1, 3 a solution to the equation 2y plus x equals y plus 4? To be clear, this is not a differential equation, so we're just looking at this algebraic expression here. The underlying assumption we make is that coordinate pair 1, 3 is identifying an x value of 1 and a y value of 3. And we would substitute those values into this equation to see if we get a true statement. So I would try 2 times 3 plus 1 on the left-hand side. And of course, that's going to give me 7. And on the right-hand side, we would have 3 plus 4, and that gives me 7. So because we get the same thing on the left and the right-hand side when I substitute in the proposed solution, then this tells me that yes, this would be a solution to this equation. And I can, of course, see another example is 1, 3, a solution to now a different equation. Let's say y squared plus x equals y plus 8. And I would approach this in the same way. So plugging in our values here, we would have 3 squared plus 1, and that would give me 10 on the left-hand side. On the right-hand side, we would have 3 plus 8, which is 11. And significantly, these two sides are not equal. So when something like this happens, we say it's not a solution. So we already have established this idea of a solution to an equation being something that gives you a true statement that 7 equals 7, right? And one that is not a solution would yield something like 10 equals 11, which we know is not true. So we can carry that over and think about a different kind of equation. So those were not differential equations. And what I'd like to do here before I kind of define differential equation is to talk about just examples. So, and we're going to see that the solution to a differential equation is no longer a coordinate pair. So by comparison, I'll say is the function y equals negative 1 over x a solution to the equation dy dx equals y squared. So very different kind of equation. And to think about that, this means that a solution to this equation would be a function such that when we take its derivative, dy dx, we get the square of the original function, y squared. The way that I can approach this, if given a proposed solution, is very similar to what we did above. So I take the proposed solution and essentially I plug it into the equation, right? So on the left-hand side, we would think about y equals minus 1 over x would imply that dy dx, using the power rule, would be 1 over x squared. On the right-hand side, starting with y equals negative 1 over x, then the square of y would be the square of the function negative 1 over x, which would yield 1 over x squared. So these two things are equal. That means that when I substitute in the function y equals negative 1 over x to this equation, we get a true statement. For all x, 1 over x squared is equal to 1 over x squared. So that would mean that the answer to our question is yes, this is a solution. We get a true statement. Like above, let's take that same function or same solution, but consider a different equation. So here we still have the function minus 1 over x. And now we want to say, is this function a solution to dy dx equals y plus x? So one side of this equation is the same. So starting with y equals minus 1 over x, the left-hand side would be the derivative, which we know is 1 over x squared. the right-hand side, if I start with the knowledge that y is negative 1 over x, well, y plus x is simply negative 1 over x plus x. And the key thing here that's very different from our algebraic equations above is in order for this to be a solution, we need the resulting left and right-hand sides to be equal for all possible input values. So it is, so it is not always true by any means that 1 over x squared is equal to negative 1 over x plus x. So this would be what would happen if I would try to take a proposed solution and find that it's not a solution to the equation. So now we're at a point where I want to take a step back and think about the notion of a differential equation. So we're going to say that an equation of the form dy dx equals g of x comma y is called a differential equation. So I want to pause here and say a few things. So I wrote this intentionally. I didn't say that a differential equation is something that can be expressed like this. So we are going to just really look at a very small subset of the topic of differential equations in this course. And in particular, there's a whole course devoted to differential equations here. In looking at this equation, it's notable that I just have the first derivative of y. Differential equations can be much more complex than this. They can involve higher order derivatives, and this we would call a first order differential equation. Again, we're not going to use that language in this course because that's going to be our primary focus. So by no means am I trying to say that every differential equation could be written in this form, but certainly something that can be expressed like this is called a differential equation. The other thing is we have this g of x comma y, which might look strange because we are not really looking at multivariable functions in this course. But that is just a general way for us to include the possibility that dy dx might depend on both x and y. So if I look back at my example here, we see such a function. So on the right-hand side, we had the function y plus x. So we saw that the derivative was defined in terms of both variables. But the other thing I'll point out is that this is broad enough, g of x comma y, that it also includes functions that only depend on x and functions that only depend on y. So again, if we look at this example, here's one that only depended on y, and I could have, say, dy dx equals x squared. So this is just a very broad way to include the possibility of both the dependent and the independent variable showing up in the differential equation. Okay, so once we have this idea, then the other thing I want to mention is a solution. And the important thing here is that we understand the idea of the solution, which I think is clear from the examples. But just to kind of round this out, we would say that y equals f of x is a solution to the differential equation dy dx equals g of xy if when you substitute f of x into the expression g of x comma y for y, so we substitute f of x in place of y, then the result is dy dx. Again, that's just a long-winded way of saying that if you plug that proposed solution into the equation, and both sides, that you get a true statement that the one side is always equal to the other. And if that doesn't happen, then we say that that function cannot be a solution. And importantly, I want to emphasize that for differential equations, we're seeing here solutions, rather than being like a coordinate pair or even a number, solutions here are functions. So we're starting this new topic. This is just an introduction here in this video, but we'll start to consider other aspects about differential equations and what we can do with those in further videos.